Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe how to compute and interpret z-scores. In a previous lecture, we talked about the normal distribution. It's a theoretical distribution. We learned the characteristics of the normal distribution, which are that it is unimodal, and the mean, the median, and the mode are all equal, that it is symmetric about the mean, the median, and the mode, meaning if you folded it in half, the two halves would be mirror images of one another, and that it is asymptotic, meaning the tails stretch to negative and positive infinity without ever touching the x-axis. The normal distribution is also completely described by the mean and the standard deviation. Completely described means that the exact shape of a normal distribution is determined by its mean and its standard deviation. Because the normal distribution is a probability distribution, this means that given the mean and the standard deviation, you can use the properties of the normal distribution to compute the cumulative probability for any value. I'll describe this in the coming slides. Another property of the normal distribution is that 99.7% of the data fall within 3 standard deviations above or below the mean. This is called the empirical rule. We can also think as the percent of the data falling within each section as the area under the curve. So, using the empirical rule, 68% of the area under the curve, or the data, are within 1 standard deviation of the mean. 95% of the area under the curve, or the data, are within 2 standard deviations of the mean. And 99.7% of the area under the curve, or the data, are within 3 standard deviations of the mean. 99.7%. This means that almost all of the data fall within 3 standard deviations of the mean. Now I want to introduce you to computing the probability of a score occurring within the normal distribution. This figure shows the area under the curve, or proportion of scores within each segment of the normal curve when it's divided up by standard deviations. The probabilities shown here in pink are provided by the empirical rule. At the bottom, below the actual bell curve, I've given the standard deviations for each section. For example, the probability of score occurrence between the mean and 1 standard deviation above the mean is 0.3413. The same probability of score occurrence falls between the mean and 1 standard deviation below the mean. We can express these probabilities as percentages too by multiplying by 100. For 0.3413, that would be 34.13%. In other words, 34.13% of the scores are between the mean and 1 standard deviation above the mean. Another way to think about it is, there's a 34.13% chance that a randomly selected score from a normal distribution will fall between the mean and 1 standard deviation above the mean. So that's for the standard normal distribution. But we know that actual distributions of data often differ in their central tendency and variability. The distributions will have a different mean and a different standard deviation from the standard normal distribution. For instance, I may have a distribution of data that I got from women who are in active labor, and I've asked them to self-report their subjective level of pain on this scale shown on the right. It ranges from 0 to 10, 0 being no pain, to 10 being unimaginable or unspeakable pain. Perhaps I average all of the women's ratings of pain and find a mean of 5.5. I compute the standard deviation and get 1.8. On average, women differ from the mean of 5.5 by 1.8 points. This is how we would interpret the mean and standard deviation in this empirical distribution. We can calculate the proportion of data that fall within 1, 2, or 3 standard deviations from the mean of a normal distribution using the empirical rule. How can we do this if our actual distributions don't have a mean of 0 and a standard deviation of 1? With the Payne distribution, which has a mean of 5.5 and a standard deviation of 1.8, I could use the mean and standard deviation formulas to figure out the scores that are 1, 2, and 3 standard deviations from the mean, but it's a little annoying to do that. Another question is, how could we compare two different distributions to one another if their means and standard deviations differ? The answer is we need to standardize. Standardize means to make the scores in each distribution comparable to each other, or to put them on the same metric. In this case, we are going to use z-scores to standardize our scores. Standard scores from different distributions are comparable to one another. Z-scores are one form of standardized scores, but not the only form. There are also t-scores. Those are another form of standardized scores. With the z-scores, every score in the actual sample distribution of scores can be transformed into a standard score. This formula shows how we can convert raw scores into standard z-scores. So let's say that we have a set of scores on a variable x. The formula that we would apply to our sample data is x minus the mean of x divided by the standard deviation from that sample. You use this formula for every score in your distribution. Let's look at an example of computing z-scores. Take a look at the distribution on the lower right. If your distribution mean was 10 and your standard deviation was 5, shown on the distribution, you could compute a z-score for the raw scores of 14, 8, and 15. In reality, you convert every score in the distribution from a raw score to a z-score. Let's just practice converting 3 scores. Note that 10 is not the mean of these 3 scores. These 3 scores come from a larger distribution of scores with a mean of 10. Here are the calculations for these 3 z-scores. I start with my distribution mean, sample mean, which is 10, and the standard deviation is 5. If you look in the table on the bottom, I've shown the calculations for each score. I take the raw score, I subtract the mean, I get a deviation. Here, the deviation column is 4, -2, and 5. And then I divide those numbers by the standard deviation, which I know is 5. This results in a raw score of 0.8, a z-score of 0.8 for the raw score of 14, a z-score of -0.4 for a raw score of 8, and a z-score of +1 for a raw score of 15. Remember that when we do these calculations, we must do the parentheses first and then do the division, according to the order of mathematical operations. Again, you actually compute z-scores for every score in your distribution. We just did z-scores for 3 raw scores from a hypothetical larger distribution of raw scores. Notice something about the computation of z-scores. So let's look at these examples. Again, in this example, the distribution's mean is 10. The raw score of 14 is above the mean, and the corresponding z-score is positive, indicated by the purple arrow. The raw score of 8 is below the mean, and the corresponding z-score is negative, indicated by the pink arrow. This makes sense if you look at the formula. If x is larger than x bar, you're going to get a positive result. Note that the standard deviation is always positive, so we know this is true. If x is smaller than x bar, you're going to get a negative result. If a raw score is the same as the mean, the z-score is 0. And 0 divided by any other number except 0 is 0. Let's visualize what we did when we converted from raw to z-scores. In our original raw distribution, the mean was 10 with a standard deviation of 5. I gave you 3 example scores from that distribution that we converted: 14, 8, and 15. We are converting the raw scores into a form of standard scores, the z-scores, using the formula shown here. Once we did that, we have changed the metric of our distribution. The 14 is now a 0.8, the 8 is now a negative 0.4, and the 15 is now a 1. The mean of the converted distribution will become 0. The standard deviation of the converted distribution will become 1. So how do we interpret z-scores? Essentially, z-scores are the deviation of raw scores from the mean, but we express the scores in standard deviation units. So, for example, the third z-score we have here is positive 1. This means that that score, the score of 15, is 1 standard deviation above the mean of 10. Positive 0.8 is 0.8 standard deviations above the mean of 10. Negative 0.4 is 0.4 standard deviations below the mean of 10. This concludes part 5 of models of error and distributions. In the next lecture, you will learn about statistical inference, types of errors in judgment we make during the process of making inference, and statistical power.